Hello everyone. We continue with part 4 for the linear algebra. We were talking about Gaussian elimination method to solve systems of linear equations, and we continue with more examples. So in this example we have a 3 by 3 system. We have x, y, and z as the unknowns in these linear systems, and we have also one more unknown parameter k here. And the question asks us to analyze the solution with respect to k. So we go ahead and start by writing the coefficient matrix as usual. The coefficients in front of x, y, and z. First equation, second, and third, we write them in this matrix of coefficients denoted by A. And then the right-hand sides of these equations are given by this B. And once we do this, now we can notice that the leading term here is 1. So we can easily multiply the first row by minus 2 and then add to the second row in order to get this term equals to 0. So we achieve this. So minus 2, that's 0. And then minus 1, minus 4, we have minus 5. And we have minus 5 here, minus 1 here. Now, another operation we can do, we can multiply, let's say, the second row with minus 2 and then add to the third one in order to get this term equals to 0. And then this becomes plus 5, 5, and k minus 10. Now, as you notice, you can simplify this second row because it is minus 5, minus 5, minus 1. So if you divide the second row by minus 5, or you can say you multiply with 1 over minus 5, these two terms will become 1, 1, and 1 over 5. And then similarly, this last row is actually 1, 1, k minus 10 over 5. So these two equations here, I mean the coefficients here are the same. So if the right-hand sides of these two equations are also the same, in other words, if k equals to 11, then effectively these two equations, second row and third row, are identical. That means effectively we have two equations in the system and three unknowns. So the number of unknowns is more than the number of equations. This gives us infinitely many solutions. So we say if this case occurs, we have infinitely many solutions. But otherwise, if the left sides are the same, but the right-hand side, if they don't agree, this time this gives us a consistency and we have no solutions. Okay? Because of this consistency, then you can never get x, y, z values that satisfy these three equations at the same time. That becomes impossible, and that means no solution to this system. Another exercise, I leave this as an exercise for you, but basically pretty much everything is given. So this is the system that you are given. You need to write this, of course, with your coefficients in the augmented matrix and the right-hand sides. But pay attention that there is an unknown parameter, just like the previous example. We have this lambda. It's an unknown parameter here. Also lambda minus 2 and lambda here. So you need to analyze the solution. You should do your row operations and obtain the simplified form, and then analyze a solution with respect to lambda. And you will verify actually that we have some critical values for lambda, 0 and 3. And if we have lambda equals to 3, you will get infinitely many solutions. If lambda equals to 3, then you will show the inconsistency, and then that means no solution. So just try this by yourself. Another example I will look at is here. We have now pay attention that the right-hand sides are all equal to 0. Actually, this type of system, linear system, where the right-hand side of each equation equals to 0, this is called as a homogeneous system. It's a homogeneous system of equations. And in the homogeneous systems, actually, we will always have at least the trivial solution as one of the solutions. Okay, there might be other solutions or not, but at least for a homogeneous system, if you plug in x1 equals to 0, x2 equals to 0, x3 equals to 0, that is always a solution to this system. And you can write down the augmented matrix as usual with these zeros on the right hand side and continue with your row operations. Like you can again notice we have 1 here, so things are relatively easy. You can multiply the first row with minus let's say with minus 2, for example, and then add to the last one, and that will give you 0, 3, 7, 0. Or you can multiply the first row with minus 3 and add to the second row. This will give you 0, 2, 4 equals to 0. And the next step, you can now think about how to get rid of this term and make it 0. But notice that this 2, 4, 0, you can simplify that, and this gives you 1, 2, 0. If you divide everything by 2, which is an feasible operation, it doesn't change our system. 1, 2, and 0, and then you can multiply the second row by minus 3 and then add to the last one to get this guy 0. So this becomes 1 and 0. So this implies basically we have 1 times x3 equals to 0. So in other words, x3 equals to 0. And from the second row, you can say 1 times x2 plus 2 times x3 equals to, the right hand side is 0. And this implies x2 is also 0, and therefore x1 is also 0. So that's the trivial solution here. Okay, so let's look at to some more examples. I think that will be easier to understand. In this example, we have now 4 unknowns and 3 equations. As you see, this system is underdefined in the sense that actually in order to be able to have a complete system, the number of equations should be the same as the number of unknown parameters, but we have less equations. But you can still go ahead and check, do the usual operations, just write the coefficients here, and then try to eliminate these terms, make them equal to 0, these terms. And we can notice that again this is 1. So if you multiply the first row with minus 1 and then add to the second one, this will become 0, 1, minus 4, 3, and 0. And then next you can multiply the first row by minus 2 and then add to the last one. Okay, that will give you 0, minus 1, 4, minus 3, 0. And now as you notice, actually if we add the second row to the third one, this will become 0, this will become 0, and this will become 0. If we go ahead. So by adding the second row to the third one, we get all these terms equal to 0. So now this is 0 equals to 0 is always true. So actually this tells us infinitely many solutions. But now if you want to represent these solutions with respect to some arbitrary parameter r and t, which are real numbers, so we can let arbitrarily, by selecting this r and t, okay, we can let x3 equals to r, x4 equals to t. By the way, this representation is not unique. In other words, you are not required to let x3 equals to r, but you can choose another, x2 equals to r or x4 equals to r, doesn't matter. because all the rest of the solution will be derived accordingly. So the solution set doesn't change, but how you represent might change. And what we are in essence, effectively, what we are doing is, as you see, we have here two equations effectively, because the third one is just a true statement in any case. Effectively, we have two equations for unknowns. So to complete the system, actually, I will need to add two more equations into this system. In that case, I can write down the solution. So in order to complete that, we add two more equations, actually, equation 1, equation 2, by these arbitrary unknown R and T, which are real numbers. So once you add these two equations, then you can write the solution for this system, because once x3 is R, x4 is T, now we can use this equation which says x2 times 1 minus 4 times x3 plus 3 times x4 equals to 0. So from this you can get the value for x2. And once you get x2, again you can use the first equation to plug in the values of x1. So this is by direct substitution. Once we do these, once we introduce these two equations, then the rest is just direct substitution to obtain an x1 and x2. And then once we once we want to write the final solution in terms of these parameters R and T, this is my x1, I already calculated here, x2, x3, and x4. And furthermore, we can represent this in terms of these parameters R and T times two vectors that represent this solution. So we can call this vector as u and v. So this gives us the solution in vector form. So we obtain the vector of x1, x2, x4, x3, and x4 is represented in this solution. There's another exercise problem for you, which is very similar, so I will not go over this, but you can test yourself and try to obtain the result like this, just to verify. Again, another exercise question. So as we already mentioned, now we can write this in a more general setting. We have already mentioned that what's a homogeneous system. So if we have all the right-hand sides are equal to 0 for this linear systems of equations, then we call this as a homogeneous system. And here notice that we have m equations and n number of unknowns. So we just use m and n to represent this in a general notation. And here, if the number of equations is less than the number of unknowns, either we have no solution or infinitely many solutions, because we might still get some inconsistency. In that case, that will give us no solution. Inconsistency means here the two equations left-hand sides are the same, but the right-hand sides are the difference. So that's a inconsistent situation, just like 0 equals to 1 is not possible. So it's a no solution case. We can still get this. Or since the number of equations is less than the number of unknowns, we will get infinitely many solutions as the second alternative, second possibility. Or if the number of equations is more than the number of unknowns, then we can get actually either no solution, unique solution, or infinitely many solution. All these three cases are possible. Here's an example: x1 plus x2 plus x3. We have two. In this example, we have two equations, but three unknowns. But this one has no solution because, as I just mentioned, the left-hand sides are the same, but the right-hand sides are different. This cannot happen. It's an inconsistency. These two basically lines or planes, they can never cross each other, so there is no solution. Another example, suppose I have these three equations this time, but two unknowns. 3 equations and 2 unknowns. And this has no solution in this case. So we cannot find any x1 and x2 that satisfies all these 3 equations at the same time. Now, in the last few slides, we introduced a few more notation about our matrix algebra terminology. One of them is the zero matrix. You might already know this, but just for completeness, we will be using this in the rest of our lectures. All the elements are equal to 0. We call this a zero matrix. And if we multiply any matrix A with the zero matrix or zero matrix times A, we get back the zero matrix. Identity matrix means we have the diagonals of a square matrix equal to 1. Okay, this is an example of 2 by 2. Here also was 2 by 2, but you can imagine 3 by 3, 4 by 4, 5 by 5. Any dimension you want. It doesn't change. So the identity matrix, if we multiply any matrix A with the identity matrix, we get back the same matrix A. Finally, this diagonal matrix means all the off diagonals are 0. So we have a matrix A. It is going to have all the off diagonal terms equal to 0. So that's the condition. So there's a small typo here. This is actually n by n. The transpose of a matrix means we write the rows as columns, or we write the columns as rows of the matrix. Let's see with an example. In this matrix A, you are given the first row as 1, 2, minus 1. So if you take the transpose, the first row will become the first column. The second row will become the second column. And similarly, the third row will become as the third column. So this is how you can take the transpose. Another example is given here with respect to this 2 by 3 matrix. So as you pay attention, this is 2 by, so we have 2 rows and 3 columns in this matrix. If we take the transpose, since we interchange the rows with columns, we will end up with 3 by 2. So I will have 3 rows and 2 columns after I take the transpose. There are a few properties of the transpose that are quite handy for us. For example, the transpose of the transpose gives us back the original matrix A. If we sum two matrices and then take the transpose, that's same as taking the transpose first and then summing these two matrices. If I have A times B transpose, this is equal to B transpose times A transpose. So the order here changes if we have multiplication of two matrices and then they are in the parentheses. But if we have a scalar multiplication, so this is matrix multiplication A and B. But if we have a scalar C, which is just a real number, so we call this as a scalar. Scalar times the matrix A, if we take the transpose, the scalar, we can take it out of the transpose. So we have C times A transpose. You can check in these examples. Let's say if I give you this as the row vector, which is also a matrix anyway. So this is 1 by 5. Okay. It's a 1 by 5 matrix. And A transpose times A, first of all, you can think about what's the dimension. A times A transpose is going to be actually a multiplication of 1 by 5 matrix with 5 by 1. So A times A transpose actually gives you just a single scalar number. Okay, actually that will be giving you a 1 by 1 real number, a scalar. Okay, But if you do A transpose A, then you will get a 5 by 5 matrix. You can check this as an exercise. And similarly, you can check A times B transpose is same as B transpose times A transpose for this specific A and B given. You can just verify this and convince yourself that our properties are actually valid. The trace of a matrix, this basically defines the sum of the diagonals. So when we say the trace of a matrix, actually we are taking the summation of all the diagonal elements in a matrix. For example, if I have the matrix A, the diagonals are 3, 6, and minus 2. So the trace, or in Turkish we use the is of the matrix A, that is given as 6 plus 3 plus 6 minus 2, that gives us 7. And finally, if you want to take the power of a matrix, I will just go over this quickly, because later on we have some very similar slides in the second part. If you want to represent the power of a matrix, then that means we are multiplying the same matrix P times. And the zero power, I mean, if we have A to the power 0, that is equal to the identity matrix. Okay, that's all for our first set of lecture notes. We will continue with our second set of lecture notes in the coming videos. Thank you for watching.